Okay, today in chemistry we're going to do molecular geometry. You might want to have your periodic table out in front of you. Okay, once you have correctly drawn the little structure for a molecule, you can determine the geometry or shape using something called the VSEPR model. VSEPR stands for valence shell electron pair repulsion. And it's based on the thought that valence electrons surrounding an atom will repel one another so that the orbitals containing these electron pairs are oriented as far apart as possible. The repulsion among electron pairs in a molecule results in atoms existing at fixed angles to each other. The angle formed by any two terminal atoms in the central atom is called the bond angle. Okay, so I've divided these into two groups. Molecules with no lone pairs on the central atom, and then we'll do molecules with lone pairs. Okay, our first up is called an AB2 molecule. AB2 molecules will have a linear shape and a 180 bond angle. This A represents your central atom. B are the atoms bonded to it, so you have two atoms bonded to it. This will occur when only two pair of electrons are shared off the central atom. It will have sp hybridization, so I'll show you hybridization in just a second. Okay, we're going to draw BeCl2. Okay, so we have BeCl2. Beryllium is in 2A, so it has two valence electrons. Chlorine is in 7A, so it has 7, but you have two of those, so 7 and 7 is 14. So we have 16 electrons available. Okay, so to show hybridization, well, let's go ahead and draw it, and then I'll show you hybridization. So beryllium, chlorine, chlorine, bond, bond. So we just use 4 electrons. That leaves us 12 or 6 pair. 1 pair, 2 pair, 3, 4, 5, 6. We have used 2, 4, 6, 8, 10, 12, 14, 16. This chlorine has 8. This chlorine has 8. This beryllium has 4. Remember, beryllium is an exception to the octet rule. Now, hybridization. So beryllium, if you draw out its structure, its electron configuration, you would say it is 1s2, 2s2. Since there's 2 electrons in the s, it can't handle anymore. So what happens is, if this is your 2s, it has 2 electrons, and then after 2s you have 2p. One of these electrons moves over to your first p. So now you have a place available in the s orbital and then one in the p. So that's why it's called sp. I don't take time to do this, so I just look at how many things are around it. So remember, you only have one s, so once you have an s, then you have to go to a p. So it's got 1 in the s and 1 in the p. Okay. Next is AB3 molecules. AB3 molecules will have a trigonoplanar shape, 120 bond angles. The 3 means there are 3 atoms bonded to your central. They will have sp2 hybridization. So we're going to draw AlCl3. Al has 3 valence electrons. Your chlorines each have 7, so that is 21, 24. So we have Al, chlorine, chlorine, chlorine. We've just used 6 electrons, leaving us 18 or 9 pair. 1 pair, 2, 3, 4, 5, 6, 7, 8, 9. We've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24. 24 available. Chlorine has 8, 8, 8. Aluminum only has 6, but aluminum has 3 valence electrons, so it is good with fewer than 8. Okay? From here to here, or here to here, or here to here, should be 120. Let's go back up here. From here to here would be your 180. So if you had a full circle, half and half. Full circle, take a third of it. Hybridization, you have 1 in your S, a P, and a P, so count your things around it. So it's going to have sp2. Okay, next is AB4. Our prefix for 4 is tetra, so these molecules will have tetrahedral geometry and bond angle of 109.5. So your central atom will have 4 atoms bonded to it. We'll have sp3 hybridization. So we're going to draw CH4. Carbon gives us 4. Each hydrogen gives us 1, but you have 4, so we have 8 electrons. So we're going to do carbon, hydrogen, 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 hydrogen. 2, 4, 6, 8, 8. Each hydrogen has 2, carbon has 8. Okay, now this does not lay flat. Instead, I'm going to put a couple of wedges in here. These 2 hydrogens are pushed behind the paper, and this hydrogen is coming out. So it's going to kind of stand up like a, for lack of a better word, like a jack when you used to play jacks when you were little, and you know how it doesn't lay, that jack doesn't lay flat on the floor. If you step on it, it hurts your foot. That's how this is going to be. So here's the thing, if you don't put wedges, you've got to remember this is not going to lay flat. And so between any 2 hydrogens, whether it's this hydrogen, this hydrogen, this hydrogen, this hydrogen, this, or whatever, should be 109.5 degrees, okay? 4 things around it. 1 goes in the S, P, 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 so it has sp3. Okay, our next one is AB5. 5 tri and bi adds up to be 5. We'll have trigonal bipyramidal shape, 2 bond angles, 90 and 120. Your central atom will have 5 atoms bonded to it. Your hybridization will be sp3d. We are going to draw PCl5. Oops. Phosphorus is in 5,8, gives you 5 valence electrons. Chlorine gives us 7, but we have 5 of them, so that's 35. Gives us 40 electrons available. Phosphorus, chlorine, 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 chlorine. So we've just used 2, 4, 6, 8, 2, 4, 6, 8, 10, excuse me, 10. Leaves us 30 electrons left over, 15 pair. 1, oops, I guess I should, okay, I'm going to start using lines to represent pairs. It goes quicker. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so this chlorine, so we've used 2, 4, 6, 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26, 28, 32, 36, 38, 40. This chlorine has 8. 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 This phosphorus has 2, 4, 6, 8, 10. So this is an expanded octet, so your central atom has more than 8. All right. Hybridization, S, P, P, P. Remember, there's only 3 P's, so now you have to go to the D. So it's going to have sp3d hybridization. Bond angles. Okay, you're going to have 2 sets. These 2 here should be 90 degrees apart. This here, I'm going to have this wedge so that this one, this one, this one, this one, all 3 of these should each have 120. Okay, our next one is an AB6 molecule. AB6 molecules will have an octahedral shape, bond angle of 90. So your central atom has 6 atoms bonded to it. It will have sp3d2 hybridization. So we're going to draw SF6. Okay, sulfur gives you 6. Each fluorine gives you 7. 7 times 6 is 42. We have 48 electrons available. So we're going to have sulfur, fluorine, 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 fluorine. We've used 2, 4, 6, 8, 10, 12, leaving us 36 electrons or 18 pair. So once again, instead of putting dots, I'm going to start drawing lines. 1 pair, 2 pair, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18. Okay, we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26, 28, 32, 34, 36, 38, 40, 42, 44, 46, 48. Fluorine has 8, 8, 8, 8, 8, 8. Sulfur has 12. It has an expanded octet. All right, we're going to have some wedges in here. So each one of these are going to be like equally spaced out. So you should get 90 degrees between any 2. So it's not surely not going to lay flat. Okay? Okay. Now, this is why Lewis structures are so important to draw the correct one. Now we're going to draw molecules with lone pairs around your central atom. So lone pairs around central atoms are also important in predicting shapes of molecules. Lone pairs strongly repel the bonding pairs, pushing them closer together than might be expected. So our first one is AB3E. So once again, the B's are your atoms bonded to it. Your E are your lone pairs on your central atom. AB3E molecules will have a trigonal pyramidal shape and a bond angle of 107. So 3 atoms bonded and 1 lone pair. Hybridization will be sp3. So think of your lone pairs of things. So it's got 4 things around it. Okay, so we're going to draw NH3. Nitrogen gives us 5. Each hydrogen gives you 1, so that's 3. So that's 8 electrons. Nitrogen, hydrogen, hydrogen, hydrogen. We just use 6. That leaves us 2 electrons left over. You cannot put them on hydrogen. They have to go on nitrogen. This pair of unbonded electrons, lone pair, will push your hydrogens closer together than you would expect. So it's going to form a triangle. It's going to make these 3 make a trigonal. It's going to form a pyramid. So your bond angle between these 3 guys is 107. You have 4 things around it, so SPP, P, so it's SP3. Okay, our next one is an AB2E2. AB2E2 molecules will have a bent shape. Some people say V, bond angle of 105. So you'll have 2 atoms bonded, 2 lone pairs on your central atom. Hybridization will be sp3 because you have 4 things around it. We're going to draw good old water. Each hydrogen gives you 1, so that's 2. Oxygen gives you 6, that is 8 electrons available. Hydrogen can't be your central, so we're going to do oxygen, hydrogen, hydrogen, 2, 4. Leaves us 4 left over. The only place we can put them is on oxygen. They're going to push these hydrogens together until they're 105 degree bond angle. Okay? And you're going to have 2, 4, 6, 8. Or excuse me, you're going to have 1, 2, 3, 4 things around it, so SPPP. Okay? And I haven't said this, but I guess I should have. If you have oxygen as your central atom, or sulfur or selenium, and you only have 2 atoms bonded, it's going to always be a bent. If nitrogen or phosphorus or arsenic is your central atom and you have 3 atoms bonded to it, it's always going to be trigonal pyramidal. So the elements in a family, well, that's what we mean. They have similar properties. That means they bond in a similar manner. Okay, if when you draw you have multiple bonds, like double or triple bonds, to determine the geometry, just treat them as single. So they're not going to affect the geometry. Okay, the last thing we want to mention is if you're looking at a molecule overall, can you say it's polar or nonpolar? So we're not talking about just between 2 atoms, we're talking about overall. So you will need to look at the symmetry and whether or not lone pairs of electrons are present on the central atom. We're going to say the molecule overall is nonpolar if it is composed of like atoms. So O2, N2, F2, CO2, nonpolar. Or if the central atom has identical atoms bonded to it and no lone pairs. So because your partial charges will balance out. So these would be symmetrical. So for instance, there are no lone pairs on aluminum here in Al3. These guys are all identical, so we would say it's nonpolar. No lone pairs on phosphorus here. These are all identical, so it is nonpolar. The same here, the same here. Okay. Now if we were to change one of these out, let's change it to fluorine, well then it would become polar. Polar molecules, if lone pairs are present on the central atom, even if it has identical atoms around it, it will be polar. Or if it had unidentical atoms bonded to it. So like for instance here, water, wherever water was at. I lost my water. Anytime you have lone pairs on your central atom, polar, okay? Or if you didn't have lone pairs on your central atom and one of these guys would be different, then it would also be considered polar. All right, so that finishes up. So now you can finish up your molecular geometry homework, and that is that covers all the topics for this chapter. Thank you.